It's one thing to say you're interested in biopsychology or say you like learning about the brain and nervous system, but it's another thing to demonstrate that deep knowledge of the subject matter. So in this video, we're going to put your knowledge to the test. Alright guys, in this video we're going to practice answering multiple choice questions that are very similar in style to the ones you'll see on the actual AP Psychology exam. Remember, roughly 2/3 of your overall AP score is the multiple choice section, so we must master this area. Now before we begin, I highly recommend to pause the video, see if you know the answer, then play and see if my answer aligns with yours. Alright, let's get to it. Number 1. Blindness could result from damage to which cortex and lobe of the brain? Alright, so what they're asking is if I lose my eyesight, right, what cortex and lobe might be damaged that causes blindness? So how do I know the answer? Well, we have to visualize and know where the lobes are. And to do this, I always imagine kind of visualizing our brain. Think of it like a giant thumb, right, just like this. And we have our eye right in the front, and we got our brain stem coming down here. So where are our lobes? Well, we have our frontal lobe, which sits right in the front of our brain, nice memory technique. Our temporal lobe, which sits right on the side by our temples, nice memory technique. Our parietal lobe sits right on top of our head, and our occipital lobe is located in the back of the brain. So which one deals with vision? Well, to know this, it is the occipital lobe. Okay? A nice memory technique is imagine this O is a giant eye. We got our pupil, we got our iris, right? That deals with vision. So how does it help us? Well, anything that is not occipital lobe, we can cross off, right? One thing I always tell my students is don't always look for the right answer, look for ones that are wrong, cross them off, and then narrow it down to 2 or 3 possible choices. So anything that is not occipital cannot be our answer. Visual cortex in the frontal lobe, well, that doesn't deal with occipital, so that can't be our answer. Letter B, visual cortex in the temporal lobe. Well, temporal lobe is not occipital. That can't be our answer. C, sensory cortex in the parietal lobe. Once again, not occipital. Letter D, visual cortex in the occipital lobe. Well, there we go. We'll keep that one just for now. And E, cerebral cortex in the occipital lobe. All right, so we have 2 with the occipital lobe, so we can narrow it down to D or E. Which one is it? Well, letter E, our cerebral cortex. The cortex is the entire wrinkled part of the brain, right? The entire cortex is the entire part of the brain, right? Everything that's wrinkled, okay? So that doesn't really narrow it down. So that is not our answer. Our answer is D, our visual cortex. Information enters the eye. It's going to synapse with the thalamus and eventually make its way to the visual cortex located in the occipital lobe. Our answer is D. All right, number 2. You eat bad sushi and feel you are slowly losing control over your muscles. And I'm going to underline that because it's obviously dealing with motor control. The bacteria you ingested from the bad sushi most likely interferes with the use of what? All right, so we ate something poorly and it's impacting the control of our muscles. So which deals with our muscles? Serotonin, insulin, acetylcholine, thorazine, or adrenaline? Well, let's start with letter A. Serotonin deals with things like mood and appetite and maybe thirst, so that is not going to be our answer. What about B, insulin? Well, insulin is a hormone released by our pancreas that deals with hunger, regulating our glucose levels. So that's not going to be our answer. All right, what about thorazine? Well, thorazine is actually not even a hormone. It is a pill. It is a drug that you take if you have psychosis or schizophrenia. So that is not our answer. And what about E, adrenaline? Well, adrenaline typically is our answer when it deals with things like stress or fight or flight. And that is not our answer. So what does that leave us? It leaves us acetylcholine, which deals with muscle movement and memory and learning. Our answer is C. All right, number 3. Paralysis of the left arm might be explained by a problem in the what? So a couple things to focus on. One is the word paralysis, which means doesn't work, right? Something is malfunctioning. And the idea is, in this question, the left arm doesn't work. And here's kind of a rule of thumb for the AP exam. If they ever talk about a directional thing, my right arm, my left finger, my left foot, they're talking about the idea that everything is crisscrossed. All right, what do I mean by that? There's a term in psychology called contralateral control, okay? So what does this mean? It means the idea that contra means opposite and lateral means side. So what is this referring to? It means that you can divide the brain into a left hemisphere and a right hemisphere, and everything is crisscrossed. The left hemisphere controls the right side of the body, okay? And what does my right hemisphere control? It controls the left side of my body, right? So if I have a stroke on my left hemisphere, the right side of my body might go numb or paralyzed, right? So whenever we're talking about right finger, left side, whatever, just think about the crisscross. This is going to lead us to our answer. So let's go back to the question. If my left arm doesn't work, okay, so here's my left arm. What does that tell you? It tells you that the right hemisphere is damaged. Does it help us to answer the question? Of course it does. Because if it doesn't deal with the right hemisphere, it cannot be the answer. So let's cross anything that is not the right hemisphere. Letter A, motor cortex in the frontal lobe in the left hemisphere. Nope, we don't want that. Remember, everything is crisscross. It can't be left arm, left hemisphere. It has to be left arm, right hemisphere. That can't be right. All right, letter B, motor cortex in the frontal lobe in the right hemisphere. Well, it says right, so we're going to keep that one. Letter C, sensory motor cortex in the temporal lobe in the left hemisphere. Nope, it says left. Let's cross that off. Ooh, just like that. Letter D, motor cortex in the parietal lobe in the left hemisphere. Once again, it can't be left arm, left hemisphere. And letter E, motor cortex in the occipital lobe in the right hemisphere. So we have right, we'll keep that one. So the answer, is it B or E? Well, we just talked about in a previous question, what does the occipital lobe do? If you're thinking vision, you're correct, which tells you that this has nothing to do with movement. So that is not our answer. Our answer is B. Our motor cortex is located in the frontal lobe in our brain. Our answer is B. All right, number 4. Which chemicals pass across the synaptic gap and increase, I like the word increase the possibility the next neuron in the chain will fire? So a couple things stand out to me. First, we have to know which chemical, right, which chemical below is going to cross the synaptic gap, that's the space between two neurons, right, synapse or synaptic gap, and cause the next neuron to fire, which tells me that sometimes it decreases, right? So sometimes they increase the likelihood, sometimes they decrease the likelihood. So let's visualize this together. Imagine we have, 3 neurons, a neuron here, and a neuron here. Well, we have an action potential that's going to travel down the neuron. And if it's stimulating, increasing the likelihood, it's going to cause the next neuron to fire by releasing all these neurotransmitters into what? The synapse or synaptic gap, which is then going to cause the next neuron to fire, right? So that's increasing the likelihood. That's going to go down the neuron and cause all these synapses to be released in the axon terminal, which causes an action potential and so on, right? So we're increasing the likelihood, increasing the likelihood, and increasing the likelihood. Does that help us with our answer? Well, it kind of does, because first, asynaptic peptides, that doesn't really mean anything. That's kind of a made-up phrase, right? Another one, let's go to letter C, adrenaline-type exciters. Also kind of made up, so we're going to cross that out. Now, could it be E, potassium and sodium? Now, that does deal with the neuron, but that actually doesn't occur in the synaptic gap. Sodium and potassium occurs within the axon, right? A depolarized state as the neuron travels down. So because that occurs in the axon, not the synapse, we're going to cross that off too. So what does it lead us to? It leads us to either B, inhibitory, or D, excitatory. Now, if we're increasing the possibility, which word stands out to you? The word excite or the word inhibit? You know what I'm thinking? I'm thinking the word excite, and that's our answer. Excitatory neurotransmitters stimulate the next neuron from firing. So what does inhibit do? Inhibit, I'll do here, inhibit stops the next neuron from firing, right? It prevents it from firing so that it doesn't reach the next neuron and things stop in its course. Our answer is B. All right, number 5. Deep or slow wave sleep is associated with which type of brainwave? All right, so we got to know what deep sleep is, or slow wave sleep, those are the same thing. And when you're in deep sleep, what kind of brain waves are actually emitting from your brain? Let's think about this. First, we have to know, how do we actually collect brain waves and measure it? An electroencephalogram or an EEG, right? An EEG. And we'll put it on your scalp, we'll put all these electrodes, right, and connect them to some sort of computer, and it's going to collect and measure all your brain waves, all right? And it might tell you if you're in maybe awake, right, like right now. It might tell you if you're in non-REM 1, it might tell you if you're in non-REM 2, or maybe non-REM 3 or 4, right? So that's kind of what an EEG does. Does that help us lead to our answer? Well, it kind of does, because what we know is that alpha and beta actually occur more in the awake stage. So we have an alpha alpha wave, and a beta wave. Beta is more awake. Alpha is more kind of, tired and relaxed. So because of that, it's not really deep sleep. You're actually quite awake. All right, so does that help us answer our question? It kind of does. A, alpha, well, that can't be right because that is more of kind of relaxed mode. B, for beta, well, remember, beta is, kind of aroused, you're awake, you're ready to go. C, delta, we'll keep that one. D, alpha and beta, well, that can't be right. That's kind of awake and relaxed. And then E is beta and delta. Now, it could be delta, but it says beta there, so we're going to cross that off, which leads to our answer, which is C, delta. And we see delta waves in, these kind of very high waves in non-REM 3 and non-REM 4. All right, number 6. Deafness can result from damage to the inner ear or damage to what area of the brain? All right, so if I lose my hearing, there might be an area of my ear that's damaged and an area of the brain. Do we know which one it is? All right, to narrow it down, let's think about our lobes. So let's do our nice thumb. Right here's our frontal lobe. Here's our temporal lobe right here. We have our brain stem sticking down, and of course our eye. Just for reference, information is coming to our eye. So where are lobes located? We have our frontal lobe, which is right in the front of our head, right behind our forehead. Our temporal lobes, which sit on the side by our temples, nice memory technique. Our parietal lobe sits right on top of our head, and we talked about our occipital lobe quite a lot today, sits in the back of our brain. So which lobe deals with hearing? We know occipital lobe deals with vision, right? Here's our pupil, think about the eye. The answer is our temporal lobe, okay? How can we remember that? Well, one memory technique is by our ears, right, our temporal lobe. Also, think about tempo in music, right? In order to hear music, we have to have our temporal lobe, and we have to know tempo, which tells us anything that is not temporal lobe cannot be the right answer. Letter A, connections between the auditory nerve and the auditory cortex and the frontal lobe. Well, that's not temporal lobe. That can't be our answer. Letter B, connections between the auditory nerve and the auditory cortex and the temporal lobe. We'll keep that one for now. It does say temporal lobe. Letter C, connections between areas of the sensory cortex. We'll talk about that in a moment. That receive messages from the ears and the auditory cortex. Well, it doesn't say any lobe, so we'll keep that one. Letter D, connections between the hypothalamus and the auditory cortex and the temporal lobe. I see temporal lobe, so we'll keep that one. And lastly, letter E, connections between the left and right sensory areas of the cerebellum. Once again, it does not say lobes, so we'll keep that one. All right, so what can we narrow it down to? Let's start with letter E. Connections between the left and right sensory areas of the cerebellum. Do we know what the cerebellum is? Well, the cerebellum sits right under occipital lobe, kind of this big little brain, okay, back here, that deals with balance and posture and coordination. Nothing to do with deafness or hearing. So because of that, that is not going to be our answer. All right, let's look at letter D. We see the word hypothalamus. We know what the hypothalamus does? Well, the hypothalamus is kind of the executive of the brain. It regulates body temperature and hunger and thirst, and it controls our endocrine system. It has nothing to do with hearing. Because of that, we're going to cross that one off. All right, what about letter C? Connections between areas of the sensory cortex. Do you know what the sensory cortex does? Well, it's right by the parietal lobe, and it receives information from the body like temperature and hot and cold and all the stuff that you might feel with your hands. It has nothing to do with hearing. Because of that, that is not the right answer. So what does that lead us? It leads us to B, connections between the auditory nerve. So here's our cochlea. The auditory nerve is going to take our action potentials away from the cochlea. And where's it going to end up? It's going to end up in the auditory cortex, which is located in the temporal lobe to process sound. Our answer is B. All right, number 7. Gonzo raised his hand to answer his teacher's question. Which part of the nervous system, all right, so dealing with the nervous system, most directly allowed him to perform this behavior? All right, so if Gonzo raised his hand, that requires muscles, right? I need some muscle movement. So let's break down the nervous system to lead us to our correct answer. Remember, the nervous system, we'll do up here, can be divided into 2 types. We have our central nervous system and what? Our peripheral nervous system. So what's the difference? Well, our central nervous system consists of our brain and our spinal cord, right? Information goes up, information goes down. This has nothing to do with that, right? So let's cross off central because that doesn't deal with muscles. We'll do central. Our peripheral nervous system is all of the nerves that go away from the central nervous system, right? Our arms and our legs, right? Kind of looks like a nice person. But let's divide this further. Our peripheral nervous system we divide into what? Our somatic system, okay? And what? Our autonomic system, okay? And the autonomic system can further be divided into our sympathetic and our parasympathetic system. Okay, so what do? Our somatic controls voluntary behavior, right? I choose to lift my arm, I choose to kick, right? So voluntary movement. Autonomic is involuntary behavior, okay? Things like heartbeat and digestion, or it might be fight or flight, our sympathetic, or calming us down, rest and digest, our parasympathetic. Does this lead us to our answer? I think it does. What about A, parasympathetic? Well, that calms our body down after fight or flight, nothing to do with muscle control. All right, what about C, autonomic? Well, that controls involuntary things like heartbeat, not muscle control. And sympathetic nervous system, that controls fight or flight or freeze, nothing to do with muscles. Therefore, our answer is B, our somatic system controls voluntary muscle movement. All right, number 8. When a neuron initially depolarizes, blank. All right, so this is kind of a big question. So we have the word neuron. We know we're talking about individual cells that communicate to each other. And we also have the word depolarizes. All right, so what is depolarization? Well, when it comes to firing of a neuron, depolarization is just another name for an action potential. Okay, that's the firing of electrical signals down an action potential. Okay, so depolarizes is our action potential. So what we're really saying is when a neuron initially fires an action potential, what happens? Well, here's our memory technique. I want you to think of a salty banana. You're like, what is he talking about? A salty banana. Why? Well, if we have a neuron, this is our axon right here. Essentially, we have sodium on the outside, right? Imagine pouring salt on a banana. So salt is, what is salt? Salt is Na. Think about our little words. Salt is Na. This is on the outside of our neuron, plus, Na plus. And what is banana filled with? Potassium, right? So what is that symbol? That symbol is a K, right? Potassium is K. Okay? So when we're talking about depolarization, salty banana, salt, sodium, and potassium. So if it doesn't deal with potassium and sodium, that can't be the right answer. So sodium items, we'll keep that as sodium. Chloride? Nope. It doesn't deal with sodium or potassium. Magnesium? Nope. Not a salty banana. Potassium we'll keep. Strontium? Nope. Can't be that. Which leads us to potassium ions flow out of the cell, or sodium ions flow into the cell. What happens when a neuron fires? What's going to happen is little channels are going to open up, and all of these sodium ions are going to rush in. Okay, they're going to rush in, and they're going to rush in all the way down the axon. This is an action potential. So what is our answer? Our answer is A. When sodium ions begin to flow into the cell, that begins depolarization. All right, number 9. The information processing theory says that dreams what? All right, so we have to know our theories of dreams. So let's run through our answers and think about which one deals with what we call information processing. We're processing information. Yes, we all dream. All right, could be A. Dreams are meaningless byproducts of how our brains process information during REM sleep. Now, there is a theory that dreams are meaningless, okay? That's called the activation synthesis theory. That is not information processing. So even though it's true, it's really dealing with activation synthesis. Could it be B? Dreams are symbolic representations of information we encode during the day. Well, guess what? Anytime you see the word symbolic when we talk about dreams, they're always talking about Freud, right? Freud's wish fulfillment, right? We wish things to happen and we have them in our dreams. So yes, it's a theory, but it deals with Freud's wish fulfillment. All right, let's go to letter C. Dreams are processed by one level of consciousness, but other levels remain unaware of the dreams. Now, that kind of makes sense, but dreams really aren't about levels of consciousness, right? It's not a movie like Inception, so we're going to cross that one off. All right, let's go to E. Dreams occur only after stressful events, explaining why some people never dream. Now, I like the first part about stress, but here's the thing. Some people never dream. That's not true. Everybody dreams. So we're going to cross that one off. Which leads to our answer is D. What is the information processing theory? It's that dreams occur during REM sleep, right? That's when most dreams occur. And the brain deals with daily stress and events. So it helps make sense of what happened during the previous day. All right, number 10. The part of the brain most responsible for making decisions is. All right, so this is just understanding how the brain works. And of course, we want to know which part of the brain helps make decisions. So let me just draw our classic, right? We know we draw this all the time. Here's our thumb, here's our brain, our temporal lobe. Here's our little brainstem going down. We have our frontal lobe, our temporal lobe, our parietal lobe, and our occipital lobe. All right, so could it be a thalamus? Well, our thalamus actually sits in this kind of little egg-shaped structure. This is kind of the secretary of the brain. It's the switchboard. It decides where things go. So it's more of kind of a regulation thing, not really about decision making. All right, what about our amygdala? Well, amygdala is kind of this almond-shaped structure that deals with kind of fear and aggression. So if we talk about fear and aggression, it may be the answer, but it doesn't. So we're going to cross that off. All right, what about the hippocampus? Well, the hippocampus is all in our limbic system. It's kind of seahorse-shaped structure that deals with memory, not decision-making, so that can't be right. We're going to cross that off. All right, let's go to E, corpus callosum. All right, what's corpus callosum? Well, if we look at the brain from a different angle, from a bird's eye view, we have our left hemisphere and our right hemisphere. The corpus callosum is actually a band of fibers that connects the hemispheres together so that we can coordinate movements and that both left and right hemisphere communicate to each other. Nothing to do with decision-making. So we're going to cross that off, which leads us to D, prefrontal cortex. Located, of course, in the front of our frontal lobe, which helps with decision-making and is the voice of reasoning and impulse control, and of course, making decisions. All right, number 11. The somatic nervous system is part of the. All right, now we already talked about this before. We have a somatic nervous system, right, with different parts. Is part of the central peripheral automatic. All right, let's kind of think about this together. We talked about this earlier. We have our nervous system divided into what? Our central nervous system and our peripheral nervous system, right? Central being our brain and our spinal cord going down, right? So that can't be our answer because somatic has nothing to do with our brain or spinal cord, or at least in the sense of this question. And then our peripheral is divided into what? We talked about this already. We have our somatic, right? That's part of our question. Our autonomic. And just for fun, do you remember what our autonomic is divided into? Our involuntary things. It is our sympathetic nervous system and our parasympathetic, right? Sympathetic is fight or flight. Parasympathetic calms us down. All right, so let's think about our answers. Let's go to letter C, autonomic nervous system. Well, the somatic is completely opposite, right? One's voluntary, one's involuntary, so that cannot be our answer. All right, what about parasympathetic? Well, that's part of the autonomic system. That can't be right. What about E, sympathetic nervous system? Well, that is also a division of the autonomic system, so that can't be right either. So instead, our answer is B. Our somatic is part of our peripheral nervous system. All right, number 12. Which of the following drugs is best described as a stimulant? All right, so we have to know drug categories and we have to know what a stimulant is. So let's think about this together. There are essentially three categories of drugs. There are stimulants, there are depressants, and there are hallucinogens. What? Stimulants, depressants, and hallucinogens. What's the difference? Well, stimulants tend to increase activity in our nervous system, right? Increase heartbeat and breathing and that kind of thing. While depressants tend to decrease heartbeat and breathing, right? And everything in our nervous system. What do hallucinogens do? They essentially alter our perception of reality. Okay, so a little bit different. So can we categorize a few of these? Of course. A is heroin. Well, heroin is a type of opiate, a pain reliever, that would fall under the category of our depressant. So that can't be right. All right, what about letter C, alcohol? Well, alcohol is a depressant. I know we think it's fun and it makes us have a good time, but it actually depresses things in our body. So that can't be right. All right, what about D, codeine? Well, codeine is a type of opiate, and it's also a depressant, so we're going to put that under depressant. A lot of depressants here. All right, and let's go to letter E, ecstasy. Now, ecstasy is typically categorized as a mild hallucinogen. Ecstasy. Now, yes, it could be a stimulant, but we're going to put it under a mild hallucinogen, which tells us that our only stimulant is B, nicotine. Okay, increases heartbeat, found in cigarettes, so B is our answer. All right, number 13. Due to brain damage, 10-year-old Jenna underwent surgery to remove nearly the entire right hemisphere of her brain. Remember I talked about before, anytime we talk about the left or right something, we're typically talking about the opposite in our answer. Which of the following observations the day after the operation best illustrates brain plasticity? All right, this is a really nice question. Now, do we know what brain plasticity is? Brain plasticity is essentially saying when you have damage to the brain, your brain is able to change or adapt to those changes, okay? Which is just a remarkable process. So a couple things we need to know to answer this question. First, and we talked about this before, right? Here's our brain, right? We have our left hemisphere and we have our right hemisphere. As I said before, remember, everything's crisscrossed, so the left controls the right side of the body, the B body, And the right hemisphere controls the left side of the body. Okay, that's important to know. We also should know what each side does. For example, our left side, we know controls language. Okay, so language and writing and speech. And our right side is known for things like, facial expression and recognizing faces and things like that. So that's important to know as well. Now, if there was damage to the right hemisphere, right, what we're really talking about is the opposite side of the body, right? If I damage my right hemisphere, my left arm is going to go numb or something like that. So what we can already eliminate is if something is on the same side, that can't be the answer. All right, so let's take a look. Jenna was able to move her left hand. We're going to keep that because it is opposite. Jenna was able to move her right leg. Well, we're going to cross that out because it's the same hemisphere. We're looking at the opposite side of our hemisphere. So let's go back to our choices. A, Jenna was able to understand what was said to her. And look, B, Jenna was able to speak. What already said this? To understand speech or to speak, what hemisphere does that occur? That occurs on our left hemisphere. Well, she had damage to her right hemisphere, so speech should not be impacted by damage to her right hemisphere. So because of that, we're going to cross A and B off. Remember, language is solely, or mostly, in our left hemisphere. All right, let's take a look at E. Jenna was able to solve a logic problem. Yes, logic is important, but it's not necessarily associated with the right hemisphere. So we're going to cross that out. Which leads C, Jenna was able to move her left hand. Remember, it's opposite of her right hemisphere. So if there's brain plasticity and her right hemisphere is working again, her left hand should work, which leads us to our answer, C. All right, number 14. A doctor examining a car crash victim in order to determine whether the crash caused structural damage, I'm going to underline that, structural damage to the brain, would use what kind of brain scan? All right, so there's a lot of questions on the AP exam about scans. All right, so you're in a car crash, there's structural damage, what scan would you use? Well, in order to answer this question, there's two things we need to know. Brain scans can be used for structure. We'll talk about that, what it means. And they also can be used for function. All right, so what's the difference? Structure is really what something looks like, right? Is there a broken bone? Is there a torn ACL? Is there a tumor, right? We're just looking at something and we're just kind of deciding if something's wrong. Function is really about activity, right? Is something working? Is my prefrontal cortex having activity, right? If I have Alzheimer's, am I having activity? So it's really what something looks like versus the amount of activity. All right, does this lead us to our right answer? Well, we're looking for structure. So if it's not in the structure box, it can't be our answer. All right, let's go to B, PET scan. Well, PET scan, positron emission tomography, helps measure activity in the brain. Right? You take this substance and things glow in the dark, so to speak. That cannot be our answer. All right, what about an EEG? Well, an EEG is also function, right? This measures, do you remember? Brain waves, right? So the function of the brain, that can't be right. All right, what about an fMRI? Well, fMRI is also function, right? Literally has the word in it, functional magnetic resonance imaging, right? This combines an MRI and a PET scan, right? So that can't be right. What about letter E? Well, E is not even part of the brain. Letter E measures things in the heart, an EKG. Okay, so that thing, there's a heartbeat. Okay, so that can't be right. Which leads us to, our answer is A, MRI. The only one, right, even if you don't know specifically what it's called or what it does, measures or looks at the structure of the brain. All right, number 15. Night terrors and somnambulism usually occur during which stage of sleep? All right, so we have a couple things of sleep disorders. We have night terrors, typically children waking up and screaming and thinking something's really terrible. And what's somnambulism? This is just a fancy name for sleepwalking. Okay, sleepwalking. So what do they have in common? They have in common that your body is moving, right? I can walk down the stairs, I can move my arms. Why is that important? Let's think about it. So here's a typical night's sleep. Let's think about our sleep. We'll start with awake, and then we go to non-REM 1, non-REM 2, and then we'll say non-REM 3 and 4, okay? And a typical night's sleep will look like this. We go through 1, 2, 3, and then we go up. And right before we wake up, what happens? We go to REM. And we repeat the cycle, a few times a night, something like this. All right, and this is what a typical night's sleep look like. So when do these sleep disorders occur? Well, let's start with A, stage 1, close to wakefulness. Well, we haven't even had enough time to go to sleep yet, let alone have a dream. So that is not going to be right. We're still right here. We're just about to go to sleep. All right, what about B, REM sleep? Well, guess what? During REM sleep, our body is paralyzed, okay? We can't move. So there's no way I can walk down if my body's paralyzed. So that tells me anything with REM sleep cannot be the right answer. REM sleep? No. C, REM sleep, but only later in the night. It doesn't matter. My body can't really move during REM sleep. So that can't be right. What about letter E? Well, sleep onset is the same thing for I'm about to go to sleep. I haven't had enough time to get into a dream yet, right? So that's not going to be our answer. So what is our answer? D, stage 4. Most sleep disorders occur down here in deep sleep. Night terrors, somnambulism, I can move my arms. This is non-REM sleep.